Question number 6. In three-dimensional linear elastic solid, the number of non-trivial stress-strain relation, which is given here, equal to 6, and the strain displacement relationship, which is equal to 6, and the number of equation of equilibrium are 3. So option C will be the correct answer. Question number 9. A spring mass damper system is given. We have to tell what is the logarithmic decrement. Logarithmic decrement is denoted by delta. Formula for the logarithmic decrement is given by 2 pi e divided by square root of 1 minus e square. E is nothing but damping ratio. Damping ratio is the ratio of damping of the system to the critical damping, and the critical damping is represented by formula of 2m omega n, where omega n is the natural frequency, m is the mass. So we can write C by 2m omega n. For a spring mass system, the natural frequency omega n is given by square root of k by m. E will equal to C divided by 2 square root of k m. By putting this value here. Now we have to find the logarithmic decrement. We have to put the value of E into the equation 2 pi e 1 minus e square. After putting this value of e, we will get 2 pi c square root 4m k minus c square. Option A will be the right answer. Question number 10. A single degree of freedom system is given with spring and mass. There are two systems, in which first system having the stiffness of K1 and the mass m. The natural frequency of the first system is given omega n is equal to 10 radian per second for the first system, and second system having the stiffness of K2 and mass is same, and the natural frequency of second system is 20 radian per second. We have to relate the value of K1 and K2. As we can see, the mass in both the system is same, and we know that the natural frequency for a spring mass system is given by K by m. So from here we can calculate what is the mass, K by omega n square. So we will use this formula to relate the value of K1 and K2. So mass of system first is equal to mass of second system. So by this formula, K1 omega n1 square equal to K2 omega n2 square. We know K1 divided by K2 will be equal to omega n square divided by omega n2 square. We know the value of omega n1 is 10 whole square, and the value of omega n2 is 20 whole square. After solving this, we will get the value 1 divided by 4. So K2 is equal to 4 K1. So option D will be the correct answer. Question number 11. Consider a simply supported two-dimensional beam, and if the beam is converted into fixed beam, then we have to tell the degree of static indeterminacy will be. As we know that the hinge support restrict the movement of beam in vertical direction as well as in horizontal direction, but it does not resist any movement about the hinge point. Any rotational movement it does not resist. So there will be a horizontal reaction and there will be a vertical reaction. In the roller support, it does not resist the movement of the beam in horizontal direction, but it does resist the movement of the beam in vertical direction. So there will be a reaction in the vertical direction. Similarly, as the hinge support, the roller support does not resist any angular movement of the beam. So here the number of unknowns are 3 for simply supported beam, 1 horizontal and 2 vertical reactions. But in this case of fixed beam, fixed end does not allow the beam to move in vertical direction as well as in horizontal direction. So there will be horizontal reaction and the vertical reaction. Similarly here also vertical reaction and horizontal reaction. Also in the fixed support, it does not allow beam to rotate about the fixed point. Reactive movement at the support. Here also. In the simply supported beam case, the number of unknowns are 3. We know that the number of equation of static equilibrium are 3. Summation of all the vertical forces equal to 0, summation of all the horizontal forces equal to 0, and the summation of the moment is equal to 0. For the simply supported beam, there are 3 unknowns and which can be solved by using 3 equation of static equilibrium. But here in the case of fixed beam, here are 6 unknowns which cannot be solved by using the equation for static equilibrium. For the case first, the degree of indeterminacy was 0 because it can be solved by using 3 equation of equilibrium. But in the case of fixed beam, here the number of unknown is 6 and the equation of static equilibrium are 3. So the degree of indeterminacy is increased by 3. Question number 26. A cantilever beam is given of length 1 meter and a transverse load at mid-span is applied of 1 Newton and the cross section of the beam is a square with 10 mm side. We have to find the deflection at the free end. So let's say A, B and C. We have to find the deflection at C. To find the deflection at the point C, we can use any method. So here I am using area moment method. We can solve for the bending moment diagram for the given loading will be linear. And the bending moment at the fixed end will be equal to PL by 2. For finding the deflection at C point, we have to take the moment of area of bending moment diagram about point C. So deflection at C will be equal to 1 by E I. We have to take the moment of this area about point C, 1 by 2 into PL by 2 into L by 2. This is area of this bending moment diagram triangle. This is like a triangle, and the moment about this point, we know that the centroid of the triangle will be from this side will be 2 by 3 into this dimension, which is nothing but L by 2. So we have to take the moment about point C of this area. So this area is given here. Now the distance 2 by 3 into L by 2, which is given here, plus this distance plus L by 2. So this term is nothing but it is the area of the bending moment diagram and moment of this area about point C. After solving this equation, we will get this value . So this will be the deflection at point C. Now we have to put the values of modulus of elasticity and I, length, and the value of the load. We have to find the deflection in millimeters. So we are putting the value in millimeters. I for a square section will be equal to B is the side of the square so after solving this, we will get the value of deflection at point C will be equal to 2.5 millimeters. Question number 27. A beam in bending which is subjected by a shear force of 1 Newton and having the solid cross section of circular section and area is given 1 millimeter whole square. You have to find the value of the shear stress at the center of the cross section. For a solid circular cross section, we know that the distribution of the shear stress is parabolic and maximum at the center, and the value of the maximum shear stress is nothing but 4 by 3 V by A. 4 by 3 shear force is given 1 Newton and area is also 1 millimeter square. So we will get the value of 4 by 3, which is equal to 1.3334 Newton per millimeter square. So the value of the shear stress at the center will be equal to 1.33 megapascal. Question number 28. A simply supported slender column is given and having the square cross section of dimension D, and the column is designed in such a way that it will buckles when the value of the stress reaches the value of yield, which is 240 megapascal, and the Young modulus for the column is given 200 gigapascals. We have to find the value of dimension of this square section in centimeters. As in the given question, it is already mentioned that the column is slender. So Euler buckling load formula is applicable, which is given by pi square E I L square. Here the effective length is equal to length of the column. We know that the stress is the force per unit area. So we can find the value of P is equal to stress multiplied by area of cross section. So we can put the value of P here. Stress into area equal to pi square E I upon L square. For the square cross section, second moment of area will be equal to d की power 4 divided by 12, and area is nothing but d square. So we can put the value of area and value of I in this equation. Pi square E d power 4 divided by 12 into length 1.57 whole square. Let's put the value in millimeters. So sigma is 240 megapascal, which is Newton per millimeter square, to pi square. From here we will cancel the extra d square. E is given 200 gigapascal, so 200 multiplied by 10 to the power 3, this will be in Newton per millimeter square into d square divided by 12 into 1.57 into 10 to the power 3 in millimeter whole square. So we have to solve the value for d. After solving this equation, question number 36, a plane strain problem is given in which the normal stress in x direction is given for 50 megapascal and the normal stress in y direction for 50 megapascal and the shear stress of 75 megapascal is given. We have to find the remaining stress and strain terms. We know that from the generalized Hooke's law, strain in x direction, normal strain in x direction is equal to 1 by E sigma x minus Poisson's ratio multiplied sigma yy plus sigma zz. As the problem is given here, it is a plane strain problem. So the normal strain in z direction will be equal to 0. So EZZ equal to 1 by E sigma z minus nu sigma xx plus sigma yy. Normal strain in z direction is 0. Then normal stress in z direction will be equal to xx plus sigma yy. So this will be equal to 1 by 3 sigma xx and sigma yy both are 450. Then this will be equal to 900 megapascal. Then the sigma z will be equal to 300 megapascal. And the normal strain in x direction will be equal to 1 divided by 200 into 10 to the power 3 terms of Newton per millimeter square, and sigma x is 450 minus Poisson's ratio sigma y 450 plus sigma z 300. After solving this, we will get the value 1 into 10 to the power minus 3, which is equal to 0.001. By checking the value of normal strain and the normal stress in z direction, option B will be the correct answer. Question number 37, in which two-dimensional state of stress is given. Sigma x normal stress in x direction equal to P, and the normal stress in y direction is equal to Q, and there is in-plane shear stress which is equal to R. We have to choose the correct Aerospace stress function which satisfies the given state of stress. As we know, the formula for the normal stress in x direction is equal to partial differentiation of Aerospace stress function with respect to y 2 times. Similarly, the normal stress is given by partial differentiation of Aerospace stress function with respect to x 2 times, and the shear stress is given by this formula. So we have to choose from the options which will give sigma x is equal to P, sigma y equal to Q, and tau xy equal to R. So if we differentiate option A with respect to y 2 times, it will give the value of Q, but sigma x is equal to P given in the question. So this option is wrong. Similarly, this option is also wrong. So we have to choose from C and B. If we differentiate the option C with respect to y 2 times, it will give the value of P, and this option will also give the value of P. Now we will check by sigma y. If we differentiate this equation B, we will get the value of sigma y equal to Q. Similarly, for here, if we differentiate this equation with respect to x 2 times, we will get the value of Q, which is same as in the given question. Now we have to choose the value of shear stress. If we differentiate the option C 2 times with respect to x and with respect to y, it will give the positive R, which is multiplied by minus, so this option will give minus R. If we differentiate this option B equation by using this formula, then the differentiation of this term will give minus R, which is further multiplied by minus this sign, then we will get tau xy equal to R. So option B is the correct answer. Question number 52. A thin-walled hollow shaft of length 1 meter with a mean radius of 5 centimeter, which can transmit the torque of 7 kilonewton meter. In question number 52, we have to choose the material such that the weight of the shaft will be minimum. This is very simple, as the density of material Y is very low. So the answer will be B. The material Y will be the best material for a shaft to have the minimum weight. In question number 53, we have to assume the safety factor of 2. We have to tell what should be the approximate thickness of that shaft with the material Y. We have to tell what should be the thickness of the shaft which is used in question number 52. The yield stress for the question number 52 was 225 megapascals, and as we know, the torque for the thin walled closed section is given by 2AQ. A is nothing but A is the closed area by the thin walled, and Q is the shear flow in the section. So this is the section and this is the shear flow, and the radius is R. So we can find the shear flow. Q is equal to, we are putting the value in millimeters, 7 into 10 to the power 6 Newton millimeter, 2 into pi R square. R is given 5 centimeter, so here it in millimeter is 50 millimeter. After solving, we will get the value of constant shear flow in the thin walled section. We will get the value of constant shear flow equal to 445.63 Newton per millimeter, and the shear flow is given by tau multiplied by T. Tau is the shear stress, this is the yield stress, and this is the safety factor. Then the safe shear stress will be 225 divided by 2 megapascal. We have to use this value here, so the thickness will be equal to Q divided by tau. So 445.63 divided by 225 into 2. We will get the value of thickness equal to 3.9611. D will be the correct answer. Thickness should be approximately 4 millimeters.